learners, I welcome you to this online session on vertical and temporal distribution of temperature of the oceans. In the previous lecture, we studied the horizontal distribution of temperature of the oceans, and in this we are focusing on the vertical and temporal distribution of the temperature of the oceans. Now, after viewing this video program, you should be able to define ocean temperature, explain factors affecting the vertical distribution of temperature of the oceans, discuss the vertical distribution of temperature of the oceans, describe the vertical temperature variations in all the major oceans, and elaborate on the temporal distribution of the temperature of the oceans. So, what is vertical distribution of temperature in the oceans? It is a fundamental aspect of oceanography, and the variations that occur in different depths of the oceans, we are focusing on that. It is governed by several interrelated factors, and these factors influence how heat from the sun is absorbed, retained, and transferred within the different layers of the ocean. Let us have a brief discussion about them. Now, what are the factors that affect the vertical distribution of temperature of the ocean? These factors are solar radiation, water density, wind and surface turbulence, ocean currents, geographical locations, seasonal variations, enclosed or semi-enclosed seas. What is water density? It is affected by both temperature and salinity. We all know that warm water is less dense and therefore remains on the surface, while cold water is denser and then it has a tendency to sink. This density-driven stratification inhibits vertical mixing and leads to the formation of thermocline. Thermocline, what is thermocline? It is a zone where the temperature drops rapidly with depth. The stability of this layering means that surface heat does not easily reach deeper parts of the ocean. Wind and surface turbulence. In regions where strong winds are present, the surface waters are stirred and mixed more deeply, and this reduces the temperature gradient between the surface and the subsurface layers where there is more mixing or there is some sort of turbulence due to winds. In contrast, the calm regions experience limited vertical mixing, allowing a strong thermocline to develop. Now, there is another factor like ocean currents. Just as it affected the horizontal distribution of temperature, it is also affecting the vertical distribution of the temperature of the oceans. Warm and cold ocean currents transport heats across the globe and can affect the temperature structure at different depths also. For example, warm surface currents can increase the surface temperature and strengthen the thermocline. Upwelling cold currents can bring cooler water from the deep ocean to the surface, disrupting the usual vertical pattern. Now, geographical location also has a tremendous bearing on the vertical distribution of temperature in the oceans. In tropical regions where sunlight is intense and consistent throughout the year, the upper ocean remains warm and the thermocline is well developed. In contrast, what happens in polar regions? The surface water is cold and the temperature may not vary significantly with depth, because in depth also we find the cold water and the surface water is also cold. So the thermocline is not developed over here, and it results in uniform temperature profile from surface to bottom in the polar areas. There is also seasonal variations, as we studied during the horizontal distribution of temperature. Seasonal variations also influence the vertical distribution of temperature. During the summer, increased solar radiation warms the surface, deepening the thermocline. In winter, surface cooling and strong winds may enhance the vertical mixing, weakening or even eliminating the thermocline in some regions. Now, the condition is totally different in enclosed or semi-enclosed seas, because enclosed and semi-enclosed seas such as Mediterranean Sea, Persian Gulf may exhibit unique vertical temperature structures. Why this happens? This is due to limited water exchange with open oceans. direct higher evaporation rates and specific climatic conditions in those areas. Now coming on to the vertical temperature layers of the oceans, we have surface layer, which is the mixed layer or called photic zone, where the sunlight can reach this zone. The thermocline layer is the transitional zone, and the deep layer is the aphotic zone where the sunlight does not reach. So, if we study elaborately the surface layer or the photic zone, it extends from ocean surface to approximately 200 meters in depth, and this layer receives direct radiation, making it the warmest part of the ocean. In the tropical regions, surface temperatures in this layer typically range from 20 to 25 degrees centigrade, and since this layer is exposed to atmospheric conditions, it shows noticeable diurnal and seasonal variations in temperature. The surface layer is also biologically active as it supports marine life and depends on the sunlight for photosynthesis, as we have already studied in the video lecture regarding the ocean resources, biotic resources. In tropical areas, this warm layer is present year round, while in mid latitude areas, it develops mainly during the summer months when solar heating is more intense. Now, coming on to the thermocline layer, this is also called the transitional zone between the upper layer and the deeper layer of the ocean. So, it lies below the surface layer and acts as a transitional zone between the warm surface waters and the cold deeper waters. This zone generally ranges from 200 to 1000 meters in depth and is characterized by rapid decrease in the temperature with increasing depth. There is a rapid decrease in temperature in this layer. Within this layer, temperatures can drop by as much as 20 degrees centigrade. The thermocline also acts as a barrier to vertical mixing, limiting the exchange of heat and nutrients between the upper and the lower layers. It coincides with the pycnocline layer, where the density of water increases rapidly with depth due to falling temperatures in some areas, changing salinity also. The thermocline plays a vital role in ocean dynamics, affecting the vertical water circulation and distributing the nutrients and marine organisms. Now, coming on to the aphotic zone or the deep layer of the ocean. It begins around 1000 meters depth below the surface and extends down to the ocean floor. In this zone, the temperatures are consistently low, typically ranging from 0 to 4 degrees centigrade. There is very little variation in the temperature because sunlight does not reach these depths and water movement is minimal here. This layer is dense and cold, and because it is isolated from surface heating, it remains thermally stable also throughout the year. In the polar regions, the cold temperatures extend from the surface down to the ocean floor, as we already discussed this, resulting in the absence of well-defined thermocline in the polar regions. Now, in this figure, you see up to 200 meters depth, uh, and from there we have the thermocline layer where the temperature of the ocean is decreasing significantly, and beyond the thermocline layer, that is after 1000 meters depth, you see again the decrease in temperature is not significant, it is very less. So it remains more or less uniform beyond 1000 meters depth. In this table you see temperature is shown and depth in fathoms is shown, like 100 fathoms or approximately 200 meters. You see temperature is 60.7 degree Fahrenheit, and as the we come to 200 fathoms, 500 fathoms, temperature decrease is significant in this region, 50.1 degree Fahrenheit, then 40.1 degree Fahrenheit, and then it is reaching 36.5 in around 1000 uh, fathoms. Okay, now from here onwards, you see the temperature is decreasing very slowly. It is 1500 fathoms. It is from 1000 fathom, it is only 36.5 to 35.3. Then again it is when you reach 2200 fathoms, it is around 35.2. So the temperature decrease after 1000 fathom is very low, less, very less significant. Latitudinal and vertical decrease. In this table, you see the latitudinal and vertical decrease of temperature of the ocean combined. You see that latitudinal zone 0 to 10 degree, 10 to 20 degree, 20 to 30 degree, 30 to 40 degree, and 40 to 50 degree, and up to 60 to 70 degree. You see the temperature is decreasing significantly from the equator towards the poles. The temperature, surface temperature is decreasing. And when you consider the depth in meters, you come down, you see 0 meters, 100 meters, 200 meters, 400 meters, and up 1000 meters is shown. Then the temperature is decreasing in the uh, 0 to 10 degree latitudinal zone. You see temperature is 26.86 degree centigrade, and then it is decreasing up to uh, 18.57, and then 10, significantly around 100 to 200 fathom there, it is decreasing from 18 to 10 degrees, and then again 400 fathoms and 800 fathoms, the decrease is not that much. So you see it is decreasing up to 1000 meters. It is decreasing, you see it is decreasing from 18.57 to 4.81, and beyond that we don't have data for, but still the temperature in the previous table also we have seen that after 1000 meters it is the decrease is not so much. Now we come to temporal variation in the temperature of the oceans. It refers to the changes in ocean temperature over different time scales. When we consider the temporal variation, we consider the different time scales like daily, seasonal, annual, and long term climatic trends. Under daily or diurnal variation in the temperature of the ocean, it refers to the fluctuation in the surface temperatures that occurs within a 24-hour period and are primarily driven by incoming solar radiation during the daytime, because it receives the sunlight during the daytime, and the loss of heat at night through radiative cooling and convective processes. So the sun heats up the upper layers of the ocean during the daylight hours, leading to an increase in temperature, while at night the absence of solar radiation causes the water to cool. The magnitude of this variation depends on factors such as intensity of sunlight, wind patterns, cloud cover, and the depth of the water body also. In shallow coastal waters, the diurnal temperature changes are more pronounced due to limited volume of water and its lower thermal inertia. Shallow water bodies such as lagoons, estuaries, and tidal pools heat up rapidly when exposed to direct sunlight and cool down quickly at night when the heat is lost to the atmosphere. This rapid heating and cooling cycle affects the marine life, influencing the metabolic rates, photosynthetic activity, and the behavior of the organisms. Additionally, human activities like dredging, industrial discharges, and climate change can amplify these temperature fluctuations, further impacting the local ecosystems. In contrast, the deeper waters, exhibit minimal diurnal temperature variations due to high thermal inertia. The deeper layers of the ocean absorb and distribute heat slowly, maintaining a relatively stable temperature throughout the day. Even though the surface waters experience heating and cooling cycles, the deeper ocean remains largely unaffected because the heat exchange is confined to the uppermost layers, typically within the first few meters. The presence of thermoclines, as we have already studied, where the layers where the temperature changes rapidly with depth, acts as a barrier and prevents the significant transfer to the lower depths. Consequently, marine organisms residing in deeper waters experience a more stable thermal environment compared to those living in shallow regions. Now, coming on to seasonal variation in the ocean temperature. The seasonal variation of ocean temperature refers to the cyclic changes in the sea surface temperature (SSTs) throughout the year, driven primarily by fluctuations in the solar radiation. As the Earth orbits the Sun, different regions receive varying amounts of solar energy depending on the tilt of the Earth's axis. During the summers, when the solar radiation is at its peak, the ocean absorbs more heat, causing the surface waters to warm. Conversely, in the winter, during reduced solar radiation and increased heat loss through the long wave radiation and evaporation, leads to cooling of surface waters. The extent of this seasonal temperature fluctuation varies depending on the latitude, ocean depth, and local atmospheric conditions. In mid-latitudinal regions, seasonal temperature changes are more pronounced due to significant differences in the solar heating between the summer and winter. During the summer months, solar radiation heats up the upper layers of the ocean, creating a well-defined thermocline, a layer where we know the temperature decreases rapidly with depth. And this stratification prevents mixing between the warm surface waters and the cooler deeper waters, trapping heat near the surface. Similarly, in winter, the cooling of surface waters leads to the increased density, causing vertical mixing and redistributes heat throughout the water column. This process reduces the temperature contrast between the surface and deep waters, making the ocean temperatures more uniform. In tropical regions, the seasonal temperature variation is relatively minimal because these are the areas that receive solar radiation throughout the year. In the near constant angle of the sun ensures that the surface water remains warm with only slight fluctuations in temperature. However, tropical regions experience monsoonal and trade wind influences, which can affect the surface density by altering ocean currents and increased evaporation rates. In some areas, seasonal upwelling events where deep, cold, nutrient rich water rises to the surface can temporarily lower the sea surface temperatures, impacting marine ecosystems and fisheries. Now, in polar regions, the seasonal temperature variations are also less significant due to extreme cold conditions prevailing there and the presence of sea ice. During the summer, the sun remains above the horizon for extended period, leading to some surface warming and seasonal ice melt. However, the high albedo or reflectivity of the ice covered waters reduces heat absorption, limiting temperature increases. In winters, the absence of sunlight results in rapid cooling and formation of sea ice, and it insulates the underlying ocean layer from further temperature loss. The seasonal melting and freezing of the sea ice significantly influences the global oceanic circulation patterns, particularly through processes like thermocline circulation, which helps in regulating Earth's climate. Now, interannual or decadal variability in the ocean temperature. Beyond daily and seasonal changes, ocean temperatures also exhibit interannual and decadal variability, which refers to the temperature fluctuations occurring over multiple years to several decades. These variations are primarily driven by large-scale ocean atmospheric interactions that influence global climate systems. Three major phenomena like El Nino Southern Oscillation, Pacific Decadal Oscillation, and Atlantic Multi-Decadal Oscillation play a crucial role in shaping the ocean temperatures, altering weather patterns, and impacting ecosystems worldwide. Now, El Nino Southern Oscillations, it is a periodic climatic phenomena occurring every 2 to 7 years in the tropical Pacific Ocean, characterized by two opposing phases like El Nino and La Nina. During El Nino, sea surface temperatures in the central and eastern Pacific Ocean becomes abnormally warm due to weakened trade winds, reduced upwelling of cold water along the South American coast. This disrupts the normal weather patterns, leading to heavy rainfall and flooding in parts of South America, while causing droughts in Australia, Southeast Asia, and India. Conversely, La Nina represents the cooling phase where stronger than the normal trade winds enhance upwelling, leading to the cooler sea surface temperatures in the eastern Pacific. La Nina is typically associated with more active Atlantic hurricanes seasons, drier conditions in South America, and wetter conditions in Australia and Southeast Asia. ENSO has far reaching effects to global agriculture, fisheries, and even socio-economic conditions due to the influence of weather extremes. You have read about this in Unit 9 in the course on climatology. The Pacific Decadal Ocean is also a long time fluctuation in the sea surface temperatures across the North Pacific, and these operate on time scales of 20 to 30 years. These have two primary phases, a warm positive phase and where the SSTs in the Eastern Pacific are warmer than average and the Western Pacific experiences cooling, and a cool negative phase when the west opposite pattern occurs. These temperature shifts influence the regional climatic conditions, including variations in precipitation and drought patterns across North America and Asia. A positive PDO phase is linked to milder winters in western North America and reduced salmon populations due to warmer coastal waters, while a negative PDO phase is associated with colder, stormier conditions and improved fisheries. The PDO also interacts with ENSHO, sometimes amplifying or weakening its effects, making the climate variability more complex. Now we have the Atlantic multi-decadal oscillation also. It is a cyclic variation that occurs 40 to 60 years, and it also affects the temperature or the of the oceans across globe. Now understanding we have long term oceanic cycles is essential for climate predictions, disaster preparedness, and resource management. And so events, for example, can have severe economic impacts on fisheries, agriculture, etc. Are primarily driven by we have long term climate changes also, which is driven by greenhouse gas emissions, carbon dioxide, methane, and other greenhouse gas levels increases, and this creates 90% excess heat. The oceans absorb heat, and then the human induced global warming have an experience on persistent warming. This warming has profound consequences on sea level rise, marine ecosystem, and ocean circulation and extreme weather events. One of the most immediate effects of ocean warming is thermal expansion, where the water expands as it warms, contributing to sea level rise. An average global sea level rise of approximately 3.3 millimeters per year in the recent decades has been seen. So, another devastating consequence of long term ocean warming is coral bleaching, a phenomena in which coral expel the symbiotic algae that provide them with energy and color. And 25% of the coral species have been affected, since coral reefs support 25% of the marine species, so they are affected. In this lecture, we have studied the vertical distribution of temperature of the ocean and the temporal distribution of the temperature of the oceans. In the next lecture, we will take up the salinity and the density of the ocean, which are the other important physical properties of the oceans. Thank you.